This city, the people in it, in fact everyone in the world, are only here by chance. You, me, and all life on Earth inherited the world after a series of disasters wiped out 99% of all species. But if it hadn't been for those catastrophes, then none of us would be here at all. 65 million years ago, an asteroid the size of Mount Everest smashed into the Earth at 60 times the speed of sound. It unleashed a series of events that wiped out 70% of all species, including the dinosaurs. This is the story of that great impact. We tend to think of evolution as a calm and orderly progression from one species to the next, but scientists have made discoveries that turn that whole notion completely on its head. They see it as a much more violent process, and one surprisingly shaped by chance. In this series, we're looking at the theories on major global disasters that nearly stopped evolution in its tracks. To put Earth's violent history in perspective, think of it like a clock. Each minute represents 3 million years. At midnight, the planet formed. Just minutes later, a cataclysmic collision created the Moon. At 8:27 p.m., the planet plunged into a killer ice age. And at 10:40 p.m., massive volcanic eruptions wiped out 95% of all species on Earth. Finally, at 11:38 p.m., the Earth suffered a catastrophic cosmic impact. A strike so large, it blasted billions of tons of debris into the atmosphere and set the whole planet ablaze. It triggered a chain of events that wiped out 70% of all life on Earth, including the dinosaurs. Now, 65 million years later, scientists are piecing together the story of the day the dinosaurs died. This is the Red Deer River Valley in the Canadian Badlands. Paleontologist Phil Curry is here to investigate one of the most significant events in Earth's history, the last great mass extinction. It was an event that changed the course of evolution and led directly to the emergence of mammals and eventually humans. Curry is hunting for the fossilized remains of the last of the dinosaurs.
The wonderful thing about these badlands is you can go almost anywhere, and at specific levels you can actually find bone in great abundance. This was picked up in less than 10 minutes. And we have things like whole claws, sometimes whole teeth. This bone, which is very, very dense and hollow, is from one of the carnivorous dinosaurs. So we can see that this is something perhaps like Velociraptor. Basically, along the Red Deer River, we have 10 million years of dinosaurian history represented. And at each level, there are different dinosaurs.
These layers of rock represent millions of years of evolution. The deeper the layer, the further back it is in time.
Well, as you can see, the rock here is actually in layers. So we have a layer of sandstone here, layer of mudstone below it, layers of coal, layers of siltstone, layers of different things, but they're all laid down horizontally, one on top of the other. In a way, it's kind of like looking at a book from the back forwards. Each one of these pages, of course, represents a different page in the history of the Earth.
Somewhere in these layers, lie clues to the death of the dinosaurs. Several feet below the surface is a layer that's intrigued scientists for generations, the Cretaceous Tertiary, or KT, boundary.
This is exactly what I was looking for. This is where we have the Cretaceous Tertiary boundary. And this is the area that for a long time we suspected would tell us something about the extinction of dinosaurs, because below the layer we have dinosaurs, and above the layer we have no evidence of dinosaurs at all.
The layer dates to 65 million years ago. It marks the exact time when the dinosaurs died out.
So this appears to be the smoking gun. This may be the layer that indicated that there was a catastrophe 65 million years ago.
Scientists have found this same layer all around the world. Below it, fossils from countless species. Above it, 70% of them are gone, including the dinosaurs. Nobody knew what caused this mass extermination until clues emerged 5,000 miles away in southern Europe. Zumaya Beach, northern Spain. Hidden within these spectacular cliffs is evidence of what scientists believe wiped the dinosaurs off the face of the Earth. Almost 30 years ago, biologist Jan Smit came to these very cliffs. He wanted to know what killed off the dinosaurs. And he thought the KT boundary layer might be the key.
I started to analyze the rocks chemically, approaching the KT boundary right there. Because I thought there must be something hidden in the rocks to tell the story how they got extinct, why they disappeared.
What he discovered shocked the scientific world. The samples contained an extremely rare metal, iridium. That is, it's rare in rocks on Earth. Most of the Earth's iridium is trapped 4,000 miles below ground in the planet's core. But it is found in meteorites and asteroids.
And when you find a high abundance of iridium, you know you have a clue to extraterrestrial material. It has to come from outer space rather than from the surface of the Earth.
He thought there could only be one conclusion. A very big object must have hit the Earth. This was the breakthrough scientists had been looking for. The iridium suggested that 65 million years ago, a massive asteroid hit the planet. At the exact same time as the death of the dinosaurs. It was hard to believe this was a coincidence. Many scientists were convinced that dinosaurs had been killed by a catastrophic asteroid strike. They had a plausible murder weapon. But to prove it, they needed to find the crime scene, the site of the asteroid impact. So scientists began a global search for an impact crater. By measuring the worldwide spread of iridium, they estimated that the crater must have been enormous, around 125 miles in diameter.
The problem with iridium is it's within the meteorite, but the meteorite is totally vaporized, and the iridium is strewn out over the whole world. It doesn't matter whether you're here or there on the surface of the planet, you find the same amount of iridium. So it doesn't tell you where to look for.
The scientists knew there'd been an impact, and they knew it was big. But where on the planet had it struck? They still didn't know. It's 11:38 p.m. on our clock of the Earth's history, 65 million years ago. 70% of all life on the planet has been wiped out, including the dinosaurs. Scientists thought this could have been the result of a cataclysmic asteroid impact. But they had no real evidence of an impact big enough to cause such mayhem. Dan Derder is a NASA planetary scientist. He specializes in the aftermath of massive cosmic impacts. And where better to come than here, one of the world's most spectacular asteroid craters. Meteor Crater, Arizona. The impact that created it happened just 50,000 years ago. Its desert location means it's one of the most perfectly preserved impact craters on the planet. Meteor Crater is many times smaller than the one that must have been made by the asteroid that killed the dinosaurs, but it does demonstrate the enormous power of even a relatively small asteroid strike. It's 3/4 of a mile across. Debris is scattered over tens of thousands of square miles. And the asteroid that did all this was just 50 meters across.
If a meteorite the size of a large house could make a crater of this size, imagine the devastation wrought by the impact of an asteroid the size of Mount Everest. That's the scale of the KT impact.
Meteor Crater was a key clue in the search for the KT strike, because buried in its wall was evidence of how cosmic impacts transform stone.
That immense impact released in energy, our modern estimates are something on the order of 1 to 10 megatons. That's the scale of the largest nuclear devices we've ever detonated. That immense impact excavated millions of tons of rock. It peeled open the desert like the petals of an immense flower and sprayed blocks of ejecta, huge masses of rock the size of a small house, for miles in every direction out into the desert.
The heat and trauma of the impact was enough to transform the rock itself, shocking and pulverizing individual mineral grains.
One sign of the violence of an impact event like this can be found in the rocks themselves. This is coconino sandstone. It's a pretty solid sandstone. It's made out of quartz grains that have been cemented together. When this rock was shocked in the impact itself, it was pulverized and broke those sand grains down into a much finer material, almost the consistency of flour. You can see here what the impact has done to that material, which has now been cemented back together in the walls of the crater. Very violent event that can turn rock into flour.
This dramatic transformation was a vital clue in the search for the location of the dinosaur strike. Next stop, Trinidad, Colorado. Derder is here to examine specific minerals in the KT boundary line. The layer contains tiny mineral crystals similar to the ones at Meteor Crater, as small as grains of salt. It's quartz, but that's not why it's interesting. It's interesting because something smashed it to bits.
So here in the KT boundary layer, this thin white clay layer deposited, we find evidence not only of the iridium, which was the original signature that something funny, something extraterrestrial is going on here. This is that layer where we also find the shocked quartz.
Shocked quartz is normal quartz, only smashed, say by something extremely heavy, traveling at many thousands of miles an hour. Only one natural phenomenon could pack enough punch to shock quartz: an asteroid impact. These tiny grains are further evidence that the Earth was hit by a massive asteroid at the time of the dinosaur extinction. But the quartz grains also took scientists a step closer to the impact site, because while the iridium was spread evenly around the boundary layer, the shocked quartz wasn't.
As we look at the thickness of this layer, here in Colorado it's about a half an inch thick or so. As we move to the southeast, however, that layer gets thicker and thicker. It grows into meters thick as we move toward the southeast, toward the Caribbean. And so the increasing amount of shocked quartz and the thickening of that layer as we move to the southeast toward the Caribbean is probably a pretty good indication that, that the impact occurred in that region of the world.
The shocked quartz pointed to an impact somewhere in the Caribbean. The trouble was, there was still no crater. Then researchers got a lucky break. In 1978, Pemex, the Mexican oil company, were surveying the Yucatan Peninsula. Geophysical data from the survey and gravity field maps revealed a giant horseshoe-shaped structure buried 3/4 of a mile underground beneath the sea off the Mexican coast. It was huge, 112 miles across, 12 miles deep, with outer impact rings stretching to 125 miles in diameter.
You see circles around each other like a bullseye. And the rings define the size of a crater. And it turns out that the largest ring was around 200 kilometers in size. And that was exactly the size of the crater which was predicted 10 years before.
It was massive, it was old, and it had all the signs of an impact crater.
They took samples during drilling. And later on the microscope we found shocked quartz. By analysis of the rocks we found high abundance of iridium.
Chichen Itza, Mexico. The Mayans worshipped here 1,000 years ago, but the land they built on was shaped by an event 65 million years earlier. The area is famous for its Mayan temples and also for its cenotes, or sinkholes. They form when limestone rocks get hollowed out by groundwater, forming underground caverns. As the cavern gets bigger, its roof weakens. Finally, it collapses, leaving an open cenote. To the Mayans, they were sacrificial pools. To us, they're pointers to a species-killing impact crater. In 1996, NASA scientist Adriana Ocampo made the connection between the cenotes and the impact. She realized that the pattern of the cenotes across the region pointed to the location of the crater.
The discovery really was like a detective story. And the cenote ring was the last piece of the puzzle that gave credence to the theory.
Cenotes normally occur along lines of weakness or faults in the bedrock. Ocampo realized that the Yucatan cenotes might not be on natural fault lines. The faults could have come from an impact. Her team studied satellite images of the Yucatan Peninsula and compared them with the oil company's maps. The cenotes were arranged in a semicircular ring, exactly matching that of the impact crater.
Here we are at the rim of the Cretaceous Tertiary Impact Crater. This cenote is one of many hundreds of cenotes that form a semicircle that is the surface evidence of the Cretaceous tertiary impact crater.
Finally, scientists had the exact location of the impact. They could begin to build up a detailed picture of the day the asteroid struck. "11:38 p.m. on our clock of Earth's history. 65 million years ago. A giant lump of rock hurtled through the solar system at 45,000 miles an hour. It was 6 miles wide and weighed about 1 trillion tons, the size of Mount Everest. And it was on a collision course with Earth. It smashed through the atmosphere and crashed into shallow seas at 20 times the speed of a bullet. The impact released 6 million times more energy than the 1980 eruption of Mount St. Helens. It set off a trail of destruction that would end with the death of the dinosaurs.
And you realize that at that size, when that asteroid impacted the Earth, at the moment it started to contact the surface of the Earth, its trailing edge was still up there at 35,000 feet. That's you know, the altitude that jetliners are flying. So we're really talking a massive object slamming into the Earth.
The initial plume of superheated gases and debris incinerated virtually all life in the impact zone. Nothing within a 1,000-mile radius stood a chance.
It literally would have been hell on Earth. This mountain of rock would have immediately, the contact point would have started glowing with a brilliance like the surface of the sun. You probably, just from the heat of the fireball itself coming in, the flesh would have been burned off your body just from the intensity of that fireball itself.
But the devastation was far from over. The asteroid landed in the water, creating a massive tidal wave, the biggest the world had ever known. And if that wasn't enough, red-hot debris from the impact rained back on the Earth, setting it ablaze. Things looked pretty bleak for all life on Earth. "65 million years ago, 11:38 p.m. on the clock of Earth's history. A giant asteroid ploughed into the seas off Mexico's Yucatan Peninsula. The impact smashed a hole right through the atmosphere. A blast wave shot out at 20 times the speed of sound. Everything within a 1,000-mile radius was incinerated on the spot. But that was just the beginning. The impact was so powerful, it blasted billions of tons of debris into the sky, setting off a chain of events that would kill off most of the life on the planet. Amazingly, with modern technology, scientists can recreate this ancient impact in the lab. This is NASA's Ames Research Center, just outside San Francisco. Planetary geologist Peter Schultz uses the facilities here to analyze what happens when an asteroid hits shallow seas. Just as scientists think it did 65 million years ago. A substrate of sand represents the sea floor, with a layer of water on top to simulate the ancient ocean.
What we're trying to do is to put an ocean in here. We're trying to cover up the land with a shallow ocean. So this is kind of like something comparable to the impact on Yucatan 65 million years ago.
To simulate the asteroid, he uses the NASA Ames vertical gun range. So powerful, it can fire a projectile at 18,000 miles per hour.
We should probably be able to see everything coming in, exploding, and then moving downrange. So that should be good. Okay, lock and load.
He raises the barrel of the gun to recreate the angle of impact. A steel ball stands in for the asteroid.
Oh, sweet. Okay, get her saved. Come on, get her saved. That is so cool. Look at this. Wait.
Super slow-motion cameras capture the impact in detail.
That is simply extraordinary. Look at that. Oh, okay. Let's see what really happened. Step through this slowly. Oh, let me go back. Look at this. Oh, this is gorgeous. Kapow! Here, now it came in this direction, slammed in. This is now vapor that's expanding, heating up the atmosphere, just turning it into fiery hot, almost as hot as the surface of the sun. It's really intense. This is the part that would have been lasting seconds and then would have translated all the way downrange. And then the crater began to form.
The effect of the impact amazes even Schultz.
If we imagine this being the Earth, our atmosphere, or if we were imagining ourselves in a jet plane 65 million years ago, we'd be flying along and we would be only about less than my fingernail height.
The simulation shows the pattern of debris ejected from the sand and water. The bullet throws up pounds of debris. 65 million years ago, the asteroid would have kicked up billions of tons.
We're talking about 500 billion tons of debris that was tossed out. We saw in the experiment that this was just these were small splatters. But imagine this being the size of buildings, larger than buildings, the size of a small city.
The material thrown up from the crater reached speeds of up to 25,000 miles per hour.
Some of the debris would have actually achieved escape speed. It would have gone faster than the Earth could hold it together, to hold it in its orbit. That material could have made it to the moon. There may be some material sent from the Earth to the moon.
At the point of impact, the temperature hit 8,000 degrees Celsius. It melted surrounding rocks and sent molten bullets flying out at supersonic speeds. Superheated 2,000-mile-an-hour winds raced from the impact site. This was hell on Earth. Any creature in the impact zone would have been incinerated in an instant.
This is worse than a horror movie. This is worse than your worst dream. It's very difficult to contain our imagination when it comes to thinking about something this scale.
Peter Schultz's recreation shows in miniature what he thinks happened next.
The shock wave from the impact itself actually causes the water to splash out. So we've already created a shock that it's the beginning of a tsunami that would have traveled all the way across the Gulf of Mexico. It would have been speeding along and then crashing on the shores in Alabama, Georgia, that whole region, and over on the western side of Mexico.
The tsunami of 2004 was around 30 feet high. The tsunami 65 million years ago would have been 10 times higher and thousands of times more destructive. A 300-foot wall of water hurtled out from the impact zone at hundreds of miles an hour. First, a superheated fireball, then a mega tsunami. Nothing within the impact zone could have survived the onslaught. And on the other side of the world, far from the impact, many dinosaurs were also wiped out. It doesn't make sense, unless the aftermath of the impact was even greater than thought. Back at the KT boundary in Colorado, Dan Durder has unearthed a microscopic clue that could explain how the impact triggered a global catastrophe.
In addition to the iridium that we see in this layer and the shocked quartz grains, we find small particles of soot. In some cases, actual charcoal. But the soot we certainly see all across the layer and in all parts of the world. And in fact, if you add up the total amount of soot in that boundary layer, it adds up to something spread globally. It's something on the order of 70 billion tons of soot. And that's roughly equivalent to, all of the Earth's vegetation going up in flames at once.
This layer of soot around the world suggests a global inferno. It seems the entire planet had burst into flames. Los Alamos, New Mexico, birthplace of the atomic bomb. Los Alamos scientist Kathy Plesko and a team at the Applied Physics Division have used supercomputers to study how an impact can incinerate a planet. They've spent 1 million computing hours constructing a 3D simulation of the KT impact. The simulation reveals for the first time how the impact would have turned the planet into a fireball. It was so powerful, it hurled over 500 billion tons of debris into the air.
A lot of it makes it up into the upper atmosphere, and some of it even makes it out of the atmosphere, and it orbits in space for a little bit and then re-impacts into the surface of the Earth somewhere else. So this debris actually went all over the surface of the Earth, and as it was coming back in, just like when you see in a meteor shower, things heat up as they come back in to Earth's atmosphere, this debris would have heated up too, but there was so much of it that it would have heated up the entire atmosphere and started forest fires just from spontaneous combustion on the opposite side of the globe.
For hours after the impact, billions of tons of superheated debris rained down on Earth. It buried the planet in burning rock and set the Earth on fire. Just minutes after the impact, the Earth was ablaze. Many animals on the far side of the world that had survived the initial blast were consumed by raging wildfires.
For the dinosaurs, anywhere on the planet would have been lethal. At that point, anything standing anywhere on the surface of the planet, even in Antarctica or Siberia on the other side of the world, would have been in real trouble. It was a very, very bad day for the dinosaurs.
Incredibly, against all the odds, a few dinosaurs did find shelter and survived the tsunami and the global fires. But even their days were numbered. The final nail in the coffin was that the asteroid couldn't have struck a worse place on the planet. At 11:38 p.m. on the clock of Earth's history, a massive asteroid struck off the Mexican coast. The impact, the tsunami, and the global wildfires wiped out 70% of life on the planet. A few hardy creatures did survive, but they faced an even greater threat: sudden and dramatic climate change.
The impact lofted all of this ash and debris and dust into the atmosphere, blanketing the entire atmosphere with a thick, opaque layer that made it night for about 2 to 6 months. You couldn't see anything. You couldn't have seen your hand in front of your face on the other side of the world for 6 months.
Dust and ash blocked out the sun. Temperatures dropped like a stone and kept on dropping, thanks to the impact's location.
If there was one place on Earth that would have been a bad place to be hit, it was Yucatan Peninsula. The fact is that that area had a lot of sulfur-bearing minerals, and that has longer-term effects on the global climate, as well as immediate poisoning in the area around it.
The blast generated incredible heat. It vaporized the rock and blasted tons of sulfur dioxide into the air. It mixed with water in the atmosphere to form sulfuric acid droplets. And that was a disaster. The droplets were highly reflective. They bounced sunlight away from the Earth and sent temperatures plummeting.
So at first, you have the dust lofted into the atmosphere, which blocks out the sun. That eventually falls back as the atmosphere convects and cleans itself out. But then you've still got these sulfur oxides up in the upper atmosphere, which reflect sunlight and cool the planet. So this prolonged the impact winter for probably another couple of years.
Temperatures dropped by around 5 degrees Celsius. Forests destroyed by fire struggled to regenerate. Eventually, the sulfur dioxide fell to Earth and temperatures returned to normal. But there was a sting in the tail. The sulfur dioxide fell as acid rain.
First, you have this 6-month-long winter where there's no sunlight at all. And then finally, you get a little bit of sunlight and the plants think, oh, good, finally, I can sprout my seeds and grow again. And then the sulfur dioxide falls as acid rain and burns all the leaves off your plants.
The food chain collapsed. The few animals that had survived the blast, the tsunami, the raging fires, and the plummeting temperatures began to starve. And the asteroid's after effects just kept on coming, as global cooling made way for global warming. The rocks the asteroid hit didn't just contain sulfur, they also contained carbon dioxide. The impact released billions of tons of greenhouse gas, the equivalent of 3,000 years of modern fossil fuel burning.
The carbon dioxide was the last effect of the impact, and it hung on for centuries, now warming the planet instead of cooling it. So the climate is then artificially warm and not returning to normal values for several centuries after the impact.
Carbon dioxide choked the planet. Temperatures increased by around 20 degrees Celsius over the next 100 years. It was global warming on a fast track.
It was a true ecosystem collapse, something that we can't even imagine at any scale today. And there was no recovery. It wasn't a bad summer. It was a devastating hundreds of years.
Temperatures soared. Much of the land turned to parched desert. Even the hardiest plants died. Herbivore dinosaurs starved to death, leaving the carnivores with nothing to eat. They died too. After 150 million years, the reign of the dinosaurs ended. And now, here we are, the supreme species on the planet. Could we survive an impact the size of the KT strike?
If something as big as the KT impact occurred now, only a portion of the world would survive. Most of North America would be wiped out. And the debris coming back through the atmosphere still would have affected them. And then the longer term effects of a sudden change in climate, maybe oscillating from something that would be incredibly warm to incredibly cold, would have been very difficult to adjust. It would have been a long time of survival.
Frankly, our prospects aren't good. Maybe it was a one-off.
Of course, it will happen again. And this is nature. This is what happens. We get hit now and then, and something that's as big as the KT impact should happen every 100 million years or so.
The bigger the impact, the rarer it is. So we could be waiting another 35 million years for another dinosaur killer. But smaller impacts are much more frequent. "50,000 years ago, a 50-meter asteroid created Meteor Crater in Arizona, devastating an area the size of Greater London. As recently as 1908, the Tunguska asteroid destroyed an area of 830 square miles. Impacts this big happen around every 100 years or so. So we're due another one soon. Scientists believe that the KT impact wiped out around 70% of all species on Earth. But despite the death and destruction, life persisted. A few species not only survived, they thrived. With the dinosaurs out of the way, new kinds of animal took center stage. One was particularly successful, the mammal. These hardy creatures survived the impact and the climate change. And one species of mammal has come to dominate practically everything: us.
The extinction of the dinosaurs clearly cleared the way, if you will, emptied the world of that particular ecological niche and gave the mammals a chance to rise to prominence. And so the extinction of the dinosaurs was sort of the crucible of human evolution, ultimately, if you will. We're here because they're not.
Golden, Colorado. Jaylin Eberly hunts for fossils in a layer just above the KT boundary. These are the bones of some of the animals that survived the impact, the fireball, and the climate chaos. They were small mammals the size of rodents, unlikely heirs to the dinosaur's crown. But the qualities that had once kept them near the bottom of the food chain now took them to the top, starting with their small size.
If we compare the KT meteorite impact to, say, something we can envision today, such as a nuclear war, the organisms that would be most likely to survive something like that are going to be the small ones, the ones that can escape the surface in some way through burrowing, living underground. They had a much higher chance of surviving than anything that would be on the surface, such as these large dinosaurs.
And these subterranean survivalists had another thing in their favour. They were omnivores. They'd eat anything.
The mammals that you have right after the KT impact, such as this fellow right here, Bioconodon, these guys are generalists, meaning they could probably eat a variety of different things. For mammals, being a generalist would be very helpful after the KT boundary because there are going to be a variety of foods on the scene, and I think if you were too specialized, the KT boundary might have been where you met your end.
Unlike the dinosaurs, they didn't lay their eggs on the ground or raise their young in exposed nests.
Dinosaurs lay eggs and their young develop in eggs and then hatch. Mammals, on the other hand, they lay their eggs on the inside, if you will, and their young develop on the inside with that added protection of the mother's body. That probably was advantageous right after the KT boundary because those young just had further protection from the environments, the elements, predators, scavengers.
A few egg layers did make it. Some were the flying dinosaurs who laid their eggs in trees. They evolved into birds. And the primitive reptiles survived, like crocodiles that buried their eggs underground. Along with the mammals, these survivors of the catastrophe flourished. After 150 million years, the dinosaurs, one of the most successful species that's ever lived, were wiped out. It was the meek, the burrowers and the scavengers who inherited the Earth, and eventually they evolved into us. It's extraordinary that we may owe our very existence to one freak event, a cataclysmic impact that turned our planet into a fireball and unleashed deadly global chaos. But if it hadn't, we might not be here at all. On the next catastrophe, humans have arrived. They too must overcome supervolcanoes, climate chaos, and cosmic impacts. But for how long?